So in this video, we'll discuss the topology of Kitaev chain model. So I remind all of us that the Hamiltonian of the chain is given by sum over n, go from 1 up to n minus 1, delta psi dagger n plus 1, plus t psi dagger n, psi n plus 1, plus the Hermitian conjugation, minus mu times psi dagger n, psi n. Now, if I go to the Nambu space, and I'm assuming now that I have a closed chain with periodic boundary condition, one can write in the momentum space the Hamiltonian in the following way: 1 over n d naught. D naught is simply the distance between two sites, psi dagger k, psi minus k, and we have this matrix in the Nambu space, in the particle hole space, which is equal to which we will call hk, k for Kitaev, of k. So this is the 2 by 2 matrix that we have to analyze in order to understand the topology of the system. So hk can be written in terms of the Pauli matrices of the in the Nambu space, tau z and tau x, in the following way: mu minus 2t cosine k d naught multiply tau z, and 2 delta sine k d naught multiply tau x. I remind you that the SSH model was very similar. It was u plus v cosine k d naught sigma x. Sigma was in the AB space, in the atomic space, plus v sine k d naught sigma y. So there are a bit different parameters here. Here mu is mu and t in the SSH model. Mu and t are related somehow, but in principle they are very similar. This was multiplied by sigma x, this by tau z. So we can actually relate them even in a more closed form. If I use the operator u, the rotation operators in the Nambu space, e to the I lambda d dot tau, and I choose tau. Tau is simply the 3 Pauli matrices in the Nambu space, tau x, tau y, and tau z, and I choose d to be 1 over square root of 3, 1, 1, 1, then, and lambda equal to pi over 3, then one can check that this is simply a rotation of tau z to tau x and tau x to tau y. So if I operate with these on hk, I will get, and of course I have to, I will get the SSH model. Of course I have to change tau sigma and to use several similar parameters so that they actually match each other. But the important thing is that we expect these two models to have the same symmetries and to have very similar topological behavior. So let's discuss the symmetries of the Kitaev chain model. So we have, remind you, we can write each fermion in terms of this alpha and beta, and we have coupling in this way, alpha and beta. Now, similar to the SSH model, we can have one mode at the end of the change if the blue coupling were 0 and we have only the white coupling, or we can have coupling on the next nearest neighbors. Then we will have 2 Majoranas at the end of the chain. That's, of course, as long as we do not have this coupling between alpha and alpha. So this is the symmetry of the problem. Now, we can have 2 modes at the end. If I have next nearest neighbor coupling, 1 mode at the end. When I have I switch off the blue coupling constant, I can have 0 if the blue, we have the blue coupling and not the white ones, or -1 or -2. So in fact, the Kitaev chain model is described by a number which is an integer number. Now, what are the symmetries? So we can have integer number of Majorana 0 modes at the end of the chain. Now, what are the symmetries of the model? It's very similar. We show that it's equivalent to the SSH model. And I just remind you that the symmetries of the SSH model were the time reversal symmetry, the sub-lattice symmetry, and the particle hole symmetry, or the charge conjugation symmetry. So this is why we use the letter C here. The Kitaev chain model will have exactly the same symmetries. Time reversal, sublattice, and particle Hall symmetry. But in the Kitaev model, the particle Hall symmetry is just the fact that we use the Nambu space. It's built in the model. We cannot change the symmetry. Unlike the situation in the SSH model, we can add local chemical potential or something that changes the symmetry. But in the Kitaev chain model, it's a built-in symmetry in the problem. Of course, the coupling alpha to alpha, that's more easy to introduce. But by definition, the Kitaev chain model will have these three symmetry: time reversal, sublattice, and particle Hall symmetry. Now we know, and you will see that in later videos, that when we have these symmetries, the system belongs to the BD1, so-called BD1 class, and is classified by an integer number z. And this is an integer number is simply the number of Majorana modes, that Majorana zero modes, that we will have at the end of the edge or at the end of the system. So now I want to discuss in more detail how the topology of the Kitaev model evolves as we change parameters. So earlier we were looking at a very special, so here we have the alpha and beta, these are the Majorana modes. One can show that when t is equal to delta, that's what we discussed earlier as a special case, then between the modes exists only, between the sites exists only coupling between beta and alpha, but there is no coupling between alpha and beta of different sites. If t is not equal to delta, that will introduce a coupling between these two Majorana modes. Pay attention that we don't have coupling between the same type of Majorana zero mode. This is the sublattice symmetry. So we can have both t minus delta and t plus delta. So I want to discuss situation in which delta over t is equal to 1/2. Everything will be measured in the per potential delta. So I assume the delta over t equal to 1/2. Unlike earlier, when we have only t was equal to delta, now I allow both of them to be present. And let's see how the system evolves, how the topology of the system changes as we change the parameters in the system. So let's first discuss the case in which mu is equal to infinity. Then we have coupling between alpha and beta in the same site. And of course, if mu is very large, then I will not have a Majorana zero mode at the end. The two end Majorana mode which sit at the same site are coupled very strongly. So this is a situation when mu equal to infinity. We simply have a fermion on each site with which are coupled very strongly. So there is no mode at the end of the chain. So let's discuss now what happened when mu over t is equal to 3. So this is the spectrum of the model now. We still have a gap in the system, and I can also calculate as a function of k, and I can also calculate the winding of d. So I remind you what it was d. So the Hamiltonian, the Kitaev Hamiltonian was mu minus 2t cosine k d naught times tau z plus 2 delta sine k d naught tau x. So we can define dz, the coefficient that multiply tau z, and dxk, the coefficient that multiply tau x, and I simply change simply want to plot this d in this plot as a function. This will be the x component, and that will be the z component, and simply want to plot d as a function of k. So d as a function of k, in this case, when mu over t is equal to 3, will behave like that. Importantly, it doesn't cause the 0. Now we continue to, so we don't expect, if it doesn't cause 0, we started from mu equal to infinity. We didn't have Majorana zero mode at the end. We changed parameter slowly. We changed it to, or we changed the parameter to mu over t equal to 3. Nothing dramatic happens during these changes. The gap is not closed, so we don't expect to see a Majorana 0 mode at the end, and indeed the winding number of D also doesn't cross the origin. So this is a trivial, so-called trivial situation when we don't have Majorana 0 modes at the end. Now let's look what happened when mu over T is equal to 2. So in this case, when mu over T is equal to 2, in this case what happens is when we calculate the spectrum, the gap is closed. Let's see what happens to D in this case. D changes in this way and it touches the origin. In this case the gap is closed, and it's closed, let's see at what point it will close. The gap closes exactly at k d naught equal to pi, as we see here. In this situation, what we'll have is not Majorana 0 mode at the end, but two chiral mode, one propagating to the right and another one to the left, exactly at this point. We can formally write them as plus minus v times the integral dx times chi. So this chi is simply a Majorana field. So this one is chiral Majorana field. And we have one moving to the left and the other one to the right. So let's see what, when we change more the coupling. Now I put mu over T equal to 1. Then what happens is that there is a new gap, reopening of a gap in the spectrum as we change the mu over T to be equal to 1. And now the vector D go around the origin. It winds the origin once. When you solve the problem to a finite, in a finite system, then you will find two Majorana 0 modes on the left-hand side and on the right-hand side with oscillations here, some oscillations here, which actually remind us that the gap was closed near kd naught equal to pi. Let's continue and change the parameters. So this is, of course, a topological situation when we have a winding of the origin, and also, I didn't show it, but when you solve the problem for these parameters, you find the eigenvalues, eigenvector, you find that there are two eigenenergies at 0, and with Majorana 0 modes that is located near the end. So one of the way to think about it is that it has some decaying length, localization length, which is called psi. So when the gap closes, psi go to infinity, and when we are in the topological situation, there is a localization length psi of the Majorana modes near the ends. So if we have a finite system, we will have an energy, a coupling energy between the Majoranas, which will be proportional to e to the minus the length of the system divided by psi. E Majorana will be proportional to that. So at infinite system, they will be decoupled. So let's go on and see what happens as we change the parameters of the system. So we give some space, and let's see what happens when mu is equal to 0. So mu equal to 0 is a special case. We already discussed that in the initial discussion of Kitaev chain model. There, what we did was to assume that mu is equal to 0 and delta was equal to t. The d vector in this case looked like a perfect circle around the origin, and in this case the localization length is simply on the last site, and we define this fermion out of these two Majorana modes, which are located at the end of the wire. For the value of delta over t equal to 1/2, we have an ellipse instead of a perfect circle, and some width to the gap of the other, to the bands formed by the other Majoranas. In the case of Kitaev chain model, at the special point delta equal to t, mu equal to delta, we have just simply straight state of the Majorana modes. So this is, of course, a topological state. We have a Majorana 0 modes at the end of the wire. This is also called in several places the sweet spot. You understand why. It's a perfect circle. The localization length is only one particular on the last side, but in reality we'll have localization length which is exponentially exponential. We have some localization lengths. The coupling between the Majoranas will be e to the minus L over xi. So let's go on. We can also discuss a situation when mu is negative, equal to -1. You see how the d vector shift to the right. We still have Majorana zero modes with less oscillations. We can continue, and that will be the final result. The gap at mu equal to -t, the gap closes again. And at mu goes to -infinity, the winding is again 0. So you see that we go from winding which is equal to 1 in the topological region to winding which is equal to 0. Either you don't encircle it for, either this d vector is to the left of the origin or to the right of the origin, but it doesn't go around the origin. And this is why being trivial or topological is related to a winding number. So the last thing I want to discuss about Kitaev model is how to get these. We said that it is described by a z number, and what I would like to discuss is how to identify this z number. In this picture, we have 2 Majoranas at the end. Here we have 1 Majorana at the end. So I remind you, this was the Kitaev model in the Nambu space. And if I rotate tau z to tau x and tau x to tau y, I can write the Hamiltonian in the following form: 0, 0, z star, and z is known as the Pfaffian of the system. Now I times z, you can check, is equal to 2 delta sine k d naught plus I mu minus 2 cosine k d naught. So if I assume that mu is larger than 0 and t is equal to delta, and they are all larger than 0, then I can just simply follow the imaginary part and the real part of iz. So for kd goes to minus pi, the vector will point in this direction, right? Kd is negative, and it's a bit negative, close to 0, but negative, and the cosine near kd naught is negative, so we have mu plus 2t, and this, by assumption, they are all bigger than 0, so it will point in the z direction. Now, at kd goes to plus pi, only the sign changes a bit sign, so this vector will point in that direction. Now, what we have to ask is what happens at k equal to 0. So at k equal to 0, let's write it. If there are two options, either mu minus 2t is smaller than 0, then the vector will point in that direction. Yes, the real part here, the sine k is equal to 0, and it points just to the negative part. The cosine is 0, so mu minus 2t is negative. And then if we start at k equal to kd naught equal to minus pi, at that point we go through at k equal to 0, we go through that point and then go back to kd naught equal to pi. We go in the long way. The winding number will be 1. Now if mu minus 2t is bigger than 0 at k equal to 0, this is the opposite thing happened. At k equal to 0 will point in that direction. That means that the vector, as we change k, goes in the short way. The winding number is equal to 0. So that we can say that we calculate the Pfaffian at the trim point, at the time reversal invariant momentum points, namely at k d equal to pi, then the time reversal operation will be, the time reversal momentum will be at minus pi, but because of the 2 pi periodicity, this is the same point. So we calculate the Pfaffian at kd naught equal to pi, and at the other time reversal point at k equal to 0, and the sign, the multiplication of the signs of the two Pfaffian at this point tells us if the winding number is 1, if it is topological, or it's 0, then it's non-topological. Now, this is the multiplication of the winding number is 0 or 1. The sign tells us if it's 0 or 1. The last thing I would like to discuss is how to get these two Majorana modes at the end from this consideration. So the only thing that we have to do is to take k to 2k. Then, as we change the system evolve, it will encircle may encircle the origin twice and not once. In this case, at k equal to pi, the vector will point in the positive direction, and so this sign of the Pfaffian will be again the same sign. So it will not tell us if we are that the z number is actually 2. It will just tell us the sign of the z factor, namely if it's even or odd. So if we will have 2k, we will go twice around the circle, and so after pi, it will be in the positive direction. The sign of the Pfaffian will be, the two Pfaffian will be equal to each other, and we'll conclude that it's not topological. So the sign of the Pfaffian just tells us if we have an even number of winding or odd number of winding, and we really have to follow this z as a function of k in order to find the actual winding of the system. So thank you, and we'll continue in the next video.